So we're going to look at a calculation that can be done on a parametric surface that ties in to one of our last surface integral conversations. And the question's written out. You might even recognize the parametric surface as something I demonstrated in a previous segment. We're going to take this parametric version of the surface 2u cosine v, 2u sine v, 4u squared, and we're going to calculate the normal vector to this surface. So there are two ways of thinking about this problem, and we've used them throughout the course, but they haven't really ever been talked about at the same time in the same place. When we talked about creating a normal vector in the functions of multiple variables unit, we talked about using the gradient to do this. So the gradient had to do with creating a vector of partial derivatives. But if you were to go back and think about what we've done even earlier than that in the course, if this is the vector in the u direction and this is a vector in the v direction, there was another way to create something that was normal or orthogonal to both of these vectors, and to create something that would stick out in the third dimension. And that was the cross product. That was a cross product. Very, very, very similar calculation. So I want to do a little quick comparison here of how these two are kind of related to each other, but save it for a little bit later. But right now I'm going to just do the calculation on this particular problem, but you're going to see me come back and visit these two again, just briefly, just to shed a little bit more light on the subject. Okay, so we want to find out what is the change of this surface in the u direction and what is the change of the surface in the v direction, and generate the cross product of those two. So the normal vector will be generated by the cross product of its two partial derivatives. That will generate a vector perpendicular to these. I just nicknamed these u and v, like this is the uv plane is kind of what I'm referring it to. This is not proper notation here. But the thought is, if I'm on the uv plane, then the cross product will build me a normal vector. And partial derivatives are not very difficult to compute. So the u partial derivative of this is going to be 2 cosine of v, and that will be 2 sine of v, and that will be 8u. Cross product, the v partial derivative will be negative 2u sine of v, derivative of cosine, negative sine. Derivative of sine is cosine. And this has no variable v at all, so its derivative is 0 since that acts like a constant. And there are so many ways of calculating cross product. If we actually had a point on this graph right now to do the calculation on, it would be really simple to just plug in values for u and v and do a numerical cross product. I want to show you the algebraic manipulation for a later purpose in our surface integrals. So I like to use my old school linear algebra notation for this. I, J, K, 2 cosine v, 2 sine v, 8u, negative 2u sine of v, 2u cosine of v, and 0. But any method you use for calculating a cross product, I've mentioned in my own classes, there are at least 3 sort of common gimmicks or tricks for doing a 3x3 determinant. And if you write it that way, or you can just memorize the cross product formula. This comes out to be 0 minus 16u squared cosine of v. This will be also negative because the j component is always its opposite sign, negative 16u squared, but happens to be sine of v. And then the k component is going to be 4u cosine squared v minus a negative, which is plus 4u sine squared v. And if you wish, that last term can be simplified to just 4u. Now, this will give you the normal vector at the place where you know a particular u and v value. What we're interested in is the algebraic manipulation to be used for something else a little bit later on. So I'm going to leave you in this raw algebra form, but you may find in various book problems where they want you to say, hey, what's the actual vector here? Give me a numerical vector. Okay, there we go.